welcome to the video here for lesson number 3 on conditional probabilities. We actually kind of already did conditional probabilities in lesson 2. We just didn't call them that. Conditional probabilities are where we are given a true fact and we want to use that condition to determine the probability. So it's almost like a restriction on the probability. So the opening exercise here talks about this this high school, and we have this problem where we want to determine whether or not more female students versus male students participate in after-school athletic programs. So there's some percentages here in the second paragraph. This paragraph tells you how to create the hypothetical 1000 table. So since it's a hypothetical table, we know that the total is going to be 1000. It says 40% of students are involved in one or more after-school activities. That's total people participating in sports. 40% of 1,000 is 400, so we'll put 400 in that first column's bottom box. It then says that 58% of the students are female. So 58% of the students are female, so that would be 580 of this hypothetical 1,000 table. And it says 23.2% of students are female and participate in after-school activities. All right, so that N word is talking about just this box here, so that would be 232 people. With just that information, we should be able to fill in the rest of the table. So if I do 580 minus 232, that's going to give me 348 in this box. 1,000 minus 400 gives me 600 in this box. If I do 400 minus 232, that's going to give me 168 here, and 600 minus 348, that's going to give me 252 here. If I do 252 plus 168, I wind up getting 420 here. Everything works out with our addition, so we are good. So using this two-way table, I could determine some probability. So it says, what is the probability that a randomly selected student is female? So this is the probability of being female, and this is for the whole survey. So there's 1,000 people in the survey. 580 of them are female. So this would be 0.580. We knew that already. It was given up here. It says, what is the probability that a randomly selected student is female and participates in after-school athletics? So the word "and" here, okay, the word "and" here tells us that we want the probability of being female and sports. We'll use F and S for sports and female. So there are 232 females that participate in sports out of the 1,000 students in the building. So we have 0.3232. It then says, what is the probability that a randomly selected student participates in after-school activity given she is female? So we're going to say, what is the probability of sports given female? So that is going to be just the females. So there are 580 females in the school. So that's going to be the bottom number, right? Because we're given the fact that it's female. So we only care about females here. And we have 232 is the number of female students that play sports. If I divide those two numbers, I wind up getting 0.400. So some of the things that we could start to determine here. For 40% of students that are female participate in sports. So that's a high percentage. If I was to do a conditional probability for the males that played sports, just to kind of figure out some stuff here, try and answer their question, it's also 40%. So the only reason why this girl, I think it was a girl, Kristen, thinks that the girls should get more playing space or available facilities is because there's just more girls in this school. It's not necessarily that there's a higher percentage of girls that play sports. I know there are more girls that play sports, but the percentage of the gender that play sports is actually exactly the same. So what we can say here is there's no dependence on gender that tells you whether or not you play sports. So one gender versus the other shouldn't get more practice facility time. So here's what we're looking at today. So what we're looking at today is we just did something on the previous page. We found the probability of something happening, the probability of two things happening simultaneously, and then the probability of something happening giving one of the other pieces happening. And all three of those probabilities are kind of linked together. So there's this rule for conditional probabilities. And what this rule helps us do is it helps us evaluate the conditional probability quicker without having to maybe make a hypothetical two-way table. If we just knew the information that was given in the previous problem, I could have found the conditional probability without making that table. Another thing that's nice about this is if you know two of the three pieces, you can find the other one pretty quickly. We'll look as we get deeper and deeper into the probability chapter at more and more probability rules, essentially. This is our first probability rule. So what is our rule? The rule is if we have a conditional probability, so what this tells us, this is A given B. So if I want to find the probability of A given B, I find the probability of A and B happening, and I divide away the probability of B happening. So essentially, I'm finding the probability of them both happening at the same time and dividing away the probability of what was given. This always will give you the conditional probability. For example, if you go back to the previous problem, if we wanted to find the probability of sports given female, we could have divided the probability of sports and female by the probability of female. Well, I knew both of those pieces of information. The probability of sports and female was 0.232. The probability of being female was 0.580. Those numbers look eerily familiar to what we found from our two-way table. And if we divide this out, we get the same exact answer. So even though we can do this in the two-way table, we can also do it using our rule. And today our job is to use the rule. We spent lesson 2 doing this without knowing the rule. So here we have another example. So here's another example where we have a classification of people, whether they're right-handed, left-handed, they can use both hands, they're ambidextrous, or they are male or female. So we're creating this kind of chart by polling people, or however we found all of this information, but now we can find some probabilities. So it says, what is the probability that a randomly selected student is female? So the probability of being female from this chart is there are 14 females in this study out of 30. 14 out of 30, if we divide those two numbers, it's probably not going to be a nice number, so we will get 0.467. Remember, probabilities, we like to round the 3 decimal places. That's usually good enough. It then says, what is the probability that a randomly selected student is female given that the student is right-handed? So the probability of female given right-handed, right? That vertical slash that I'm making between F and R means given. So to find that, we would need to find the probability of F and R and divide that by the probability of what was given, R. Now I know we can just look at the chart. We could just look at the chart and say, what are the right-handed people? How many of them are female? And do it just like we did in lesson 2. The goal of today's lesson is to be able to use this new rule because we are going to need it as we move forward in the chapter. So the probability of being female and being right-handed, there are 12 right-handed females out of 30 people in the survey. Then the probability of being right-handed, there are 23 people in the survey out of 30 that are right-handed. If you divide those two fractions, use your parentheses in your calculator, you're going to get 0.522. We would have got the same thing if we just said, let's just look at right-handed people. How many are female out of the total? 12 out of 23 would be that same exact decimal. I know that, right? The goal here, though, today is to see that this formula or this rule actually works too. So then it says, how did knowing that the student is right-handed affect the probability of picking a female? Well, what we can see here is by knowing that the person's right-handed, the probability increased slightly. Right? So what we can say is actually a couple different things. We can say there's a greater chance of being a female if you're right-handed, right? You could say that the probability increases of picking a female when only looking at right-handed people versus left-handed people in this small sample. All right, so all of those things you can write here that I just spoke about, I'm not going to write them all out. All right, so here's another two-way table. This one talks about a nonprofit organization encouraging members to determine their vacation destinations. So you can see it's not all about just being males and females. This could be a lot of different things. So we have the person watched the ad online or did not watch the ad online, plans a vacation in New York or does not plan a vacation in New York. So one of the things that we want to be able to do here is find these probabilities. Again, keep using these rules whenever we can. So it says, what is the probability that a randomly selected person will vacation in New York within the next year? So out of the people that plan to vacation in New York, we'll just call that New York. There are 400 of them out of the hypothetical 1,000 table that they've created for us. So we have 0.400. About 40% of people are going to plan to vacation in New York. What is the probability that a randomly selected member will vacation in New York given that they watched the ad? Now, this is interesting. We know that 40% of people are going to plan on coming to New York for vacation. If we add this added stipulation of given that they watched the ad, if this probability goes up, what we can kind of justify is that the ad made more people want to come to New York. If it made it go down or stay about the same, we could say the ad really didn't mean anything. So we can say, what is the probability of vacationing in New York given watching the ad? I'm just going to write this all out words because they didn't really give us symbols. You could use the given mark if you want. So that would be the probability of New York and watching the ad. So that's 300 people out of 1,000. Divided by the probability of people that watched the ad. So there were 750 people out of the 1,000 that watched the ad. So if I do those two fractions divided, I get 0.400. Notice these numbers are the same. So because the people that watched the ad had the same chance or the same probability of coming to New York for vacation, do you think that the ad actually made a difference? So it says, do you think that the ad campaign is effective? The answer to that is no, because the probability of a New York vacation did not increase if you watch the ad. So because the probability didn't change at all even, it means that the ad was irrelevant, right? It didn't actually help more people come to New York. All right, so here's where we're trying to get to. So what we want to be able to get to is I want to be able to create some probabilities without actually having to make a two-way table. Because in all reality, you're going to have a problem. You're going to want to solve it quickly. You're not going to want to create a two-way table if you have all the information you can to be able to find a conditional probability. So it says Mr. Hines determined that the senior class, 15.3% of members are in the drama club. So we're going to say the probability of being in drama is 15.3%. So we'll say 0.153. We like decimals better than percents here. It then says that 10.2% are in AP calculus. So we're using C for calculus. We'll call that 0.102. And the probability of both, so we'll say D and C, is 0.015. 1.5% is 0.015. So it says determine the probability of D given C. The probability of D given C. Well, that would be the probability of D and C divided by just the probability of C. So we're saying both happening with end, and then we're dividing by whatever the probability of what was given was. So since we already know these numbers, the probability of DNC is 0.015. The probability of C is 0.102. Type that in the calculator, 0.015 divided by 0.102. That gives us the decimal 0.147. says to show it as a percent, so we'll say 14.7%. So then it says, Mrs. Imperato would like a basic interpretation of these results. Write a statement relating your calculated probabilities to student enrollment in the given situations. So a couple things that we can notice from this particular probability. So it says 15.3% are in drama, 10.2% are in AP calculus, only 1.5% are in both. But the probability of being in drama, given that you're in AP calculus, made it so that this decimal or this percentage was higher than the AP calculus number. So what we can say here is there's some type of a correlation between the courses that you take and whether or not you're in drama, because the probability changed, right? The probability of whether or not you're in AP calculus is affecting the probability of whether or not you took drama because of this conditional probability. So whether that effect is a positive effect or a negative effect, that's an AP stats question. For us, we just have to notice that there's a difference, that there's a change, right? So what we can say here is there is some type of an effect that whether or not you're in drama club is going to affect whether or not you take AP calculus or vice versa. And that is what you can write here. Number 4 says the probability that a new microwave oven will stop working in less than 2 years is 0.05. The probability that a new microwave oven is damaged during delivery and stops working in less than 2 years is 0.04. And the probability that the new microwave is damaged is 0.10. So let's say stop working, we'll use the variable S. And damage during delivery, we'll use the variable D. We want to say those variables somewhere. You don't have to make let statements like you're back in algebra, but you want to state something somewhere or use ones that are realistic. So we know that the probability that it stops working is 0.05. The probability that is damaged during delivery, the probability is damaged during delivery was 0.10, and the probability that it stopped working and was damaged was 0.04. It says, given that the new microwave was damaged during delivery, what is the probability it stops working in less than 2 years? So the probability that it stops working given that it is damaged, so we would say the probability of S and D divided by just the probability of D. So we knew that the probability of S and D was 0.04. And the probability of just D was 0.10. All of that was given information to us. If I do 0.04 divided by 0.10, I get 0.4. So the probability of stop working, given the fact that you were damaged, is 0.40. So a 40% chance. Well, that is way different than the probability of it just stopping working. So what we can say here is that the fact that this was a damaged microwave affected whether or not it stopped working actually greatly, right? That's a big increase. Again, right now for this class, all we need to notice is that there is a change here, right? We don't need to notice if it's a a positive correlation or anything like that. We just need to know that there's some type of change happening. If you got that, you got the lesson. All right, so this is a good opportunity for you to pause the video, come back. We'll talk about party registrations and some conditional probabilities in the homework. But again, it's important that you're trying these questions first before you just jump right in and complete the whole video. So go ahead, pause the video and come back. All right, welcome back. Hopefully you tried these on your own. So what we can see here is we have this two-way table talking about the 3 different parties, W, X, and Y, and whether or not you're male or female. What I like to do is when there is good variables like W, X, and Y, I'll use those. Male and female, those are easy. We'll just use F and M. But I like to just put them right in the table. It just shows that I know what variables I'm using. So it says, what is the probability that a randomly selected voter is in party Y? So the probability of a party Y voter, there are 500 people in the survey, and of those, there are 168 that are registered for party Y. 168 divided by 500 is 0.336. It then says, given that the voter is male, what is the probability that they are registered for party Y? So the probability of voting registered Y, given that you're male, that's going to be the probability of Y and male divided by just the probability of male. I know you can do this conditional probability just using the table, and if you did it that way, good for you. But I want to practice the skill of this new rule. So the probability of Y and M. So Y and M, there are 48 out of 500. Probability of just being male, there are 200 out of 500. So if I do some quick calculations by dividing those fractions, I get 0.240. So we can see here is by knowing that the voter is male, this probability decreased somewhat. So does knowing that the voter is male affect the probability? The answer is yes, because the probability is different when you include the fact that it is a male voter. So the answer here is just plain old yes, because the probabilities changed. So we could say the probability is affected by male voter. I'm pretty sure I used the right affected. It might be the one with an A. I'm going to use the one with an E. I don't really know the difference. So it then says, given the randomly selected voter of party Y, what is the probability that they are male? Now, you might think that these two questions are the same, but they are different. So this is actually the probability of male, given that it is a voter for Y party. So it's going to be the probability of male and Y. That's going to be the same fraction, 48 voters out of 500. But the dividing fraction, or the denominator, is going to be different, right? What's the probability of being a Y voter? So Y voter was 168 out of 500. So I could say 168 divided by, I'm sorry, I did that totally wrong. 48 over 500 divided by 168 over 500. What we could see here is that this probability is also different. So we could say here is the probability is different. So these two probabilities here and here are different, meaning that there's something happening when we have these males that are part of party Y, right? So there's a higher chance if you're male that you would choose party Y, or if you were in party Y, there would be a higher chance that you are in fact a male. Okay, so whatever party Y is talking about is probably more appealing to males than females in some way. And that's it. Pretty easy homework assignment, pretty quick video. If you have questions, please reach out to me via email, and we'll hopefully see you soon.